Good afternoon, everybody. Thanks for joining us today. We'll be getting started in just a minute here. We've had a surge of participants joining, so we want to make sure that we've got as many people in as are joining, and then we'll get started.
Well, good afternoon. I'm Ryan Siegel. I'm joined today by my colleague Sean Maurer. We're here from the Smart Energy Design Assistance Center at the University of Illinois at Urbana-Champaign. Just a reminder, today's session is being recorded and will be posted to our website after today's presentation. Today's session will be approximately an hour and a half long, and if you do have any questions throughout our presentation, feel free to enter those using the question and answer pane that you may find towards the bottom of your screen. So if you do post questions there, we'll be able to see them and either answer them as a course of the presentation or towards the end of the presentation, we will plan to have some time for questions and answers. So a little bit about today. We will note that some of the differences between ASHRAE 2019 and the IECC is also changes that are being made between the 2018 IECC and the 2021 IECC. So many of you are going to get a preview today of what is going to be coming here to the state of Illinois. Do have a few learning objectives. Obviously, we're going to be looking at the differences and similarities between IECC and ASHRAE 90.1, and particularly focusing on HVAC and service water requirements, as those are closely related. So today you will have continuing education credits for today's presentation. Everyone who is attending today's session will receive a certificate of participation following today's session in your email. If you do need ICC or AIA credits, in that email there will be a link that you can fill in a form so we can go ahead and get those recorded for you as well. But you don't necessarily need to email us initially to get those. It takes approximately 1 week for those certificates to come out. So everyone today will get a certificate of participation. For those of you who may be needing continuing education credits that are for other than ICC or AIA that may use self-reporting methodologies, you'll have that for your records. So a little bit about who we are. As I noted, we are part of the University of Illinois, and our primary mission is to reduce the energy footprint of the state of Illinois and beyond. And so part of how we do that is through our Energy Code training program. We are the Energy Code training provider for the state of Illinois, and today's training is sponsored in part by the Illinois State Energy Office at the Illinois Environmental Protection Agency. So we do want to thank them for helping to make today's presentation possible. In addition to today's presentation that is being recorded and will be posted to our website, PDFs will also be available on our website as well. So you'll be able to have those slides for your reference. As far as we are here to provide technical support for the Illinois Energy Conservation Code. So if you do have questions and need some technical assistance, feel free to reach out to us at energycode@illinois.edu. Or if you have just a quick question, we do have an 800 number that you may use. This is available for any projects for the state of across the state of Illinois, be it code officials, design professionals, project teams, and even building owners and occupants. We also have several online resources at our website, and some of those do include archive versions as well as upcoming workshops and webinars. We do have several online on-demand training courses. These cover a broad array of energy code topics, uh, along with links to our technical support line. So if you can't recall the 800 number or our email address, energycode@cdac.org, you can find that also at our website. We also have several other resources, including some explanations about the Illinois Energy Conservation Code, several frequently asked questions, and links to several useful websites. So this is very useful for links to the International Energy Conservation Code, which is the basis of the Illinois Energy Conservation Code, Illinois amendments, and the Chicago Energy Conservation Code. So rather than trying to recall a big long string of a web address, again, you can come to our website, cdac.org/energy-code. So ASHRAE does provide access to their online access to their standards, so you can view preview versions of the ASHRAE standards. The most current that will be towards the top of their page is the standard 2019 for ASHRAE 90.1. Presently in force in the state of Illinois is the 2016 ASHRAE 90.1, which can be found further down the page on ASHRAE's website here. So if you do a search for 90.1, the first one you'll likely come to on the page will be the 2019, and then if you continue your search, it'll drop you down in the page and you can find the previous versions that you can view online. These are view onlys. They're not designed for copy and paste of text, but at least you do have a way to view them if you're less familiar with it. A little bit about the differences between ASHRAE 90.1 and the IECC is ASHRAE 90.1 is a standard, whereas the International Energy Conservation Code is a code. So either of these may be used for energy code compliance. The IECC is the adopted code of the state of Illinois, and many jurisdictions across the country. The IECC also allows for the ASHRAE standard to be used, to be shown, to demonstrate code compliance for your project. The important thing here is you have to demonstrate energy code compliance using either the ASHRAE standard or the IECC code. Either one is acceptable, but all compliance has to be demonstrated with one or the other. So, today's session is part of a series of workshops. Today we're covering mechanical and some surface water heating. Coming up, we have lighting and electrical in November, and then performance-based compliance coming up in December. So if you want to register for those, we do have the links here for upcoming webinars and workshops. As far as the 2019 version, understanding that the 2019 version of the 90.1 is already 2 years old. However, this will become enforced here in the state of Illinois with the planned adoption of the 2021 International Energy Conservation Code next year. It is anticipated that that will be enforced sometime in the summer of 2022. So we have seen that some clients have elected to use a newer version of the standard to increase their energy savings, and that Department of Energy even determined the 2019 version saves nearly 5% as compared with the previous 2016 version. Uh, However, before you assume that you can use the newer version, uh, we do encourage you to have a conversation with your code official, as they may require compliance to be shown with the 2016 version, because they may not be up to speed with the 2019 changes. It's a little less common in the energy code, uh, where code officials will encourage or will require an older code to be used, and not perhaps allow the newer code to be used for demonstration of code compliance. However, that's because there's not as much interplay with the energy code as there is with the other building codes. So using a newer energy code is not likely to have a substantive impact on compliance with the energy code. Also understanding that many jurisdictions, because most compliance is demonstrated, use the IECC, there may be some learning curves for the municipality for 90.1, regardless of if you use the 2016 or the 2019 version. As far as the organization, just a real brief thing as far as the IECC. The front end is setting up, the code, the purpose, and the scope, then getting into definitions and general requirements. And then chapter 4 is really our meat and potatoes for the IECC. And chapter 5 is where IECC places existing building requirements. So with the IECC putting the existing buildings as a separate chapter. With ASHRAE, again, similar up front, purpose and scope, definitions and admin. However, existing buildings for ASHRAE are in the individual components. So building envelope, HVAC, lighting and service, hot water, existing buildings are within those sections as well. And then they've pulled energy cost budget as a separate item for ASHRAE. So as far as our series, we do cover, our series is going to cover sections 5 through 10 of ASHRAE 90.1. Building envelope was our previous session, and that is archived at our website. Today covering HVAC and service hot water, power, lighting, and other equipment will be coming up in the future. So on November 9th. A little bit as far as the organization of ASHRAE 90.1 for HVAC. Section 6, this is kind of a flow chart where ASHRAE at the beginning of each section does have give you a little bit of a flow chart as far as helping you work through the compliance and what you have to follow, showing here that if you are following section 6.3, that bypasses the need to follow 6.4, 6.5, 6.6, section 11, and appendix G. So here's a few different paths for compliance that you have rather than the specific components. So a little bit of a difference in layout. Something we do want to call out is there are a few differences in the climate zones between the International Energy Conservation Code and ASHRAE 90.1. So here in the state of Illinois, there are 6 counties in the state of Illinois that under ASHRAE 90.1 have moved to a warmer climate zone 4. So this is one of the differences that IECC in their 2021 is going to be updating their climate zone map to bring it in line with ASHRAE 90.1. So this is definitely a preview. So if you do live in one of these or have projects in one of these 6 counties, be aware that that may be a difference for your project. So Before we get too far in, we would like to learn a little bit more about you and your experience with ASHRAE 90.1 versus IECC. So we do have a poll question here for you. First question is, have you used or seen the 90.1 compliance options? And question number two, how comfortable are you with 90.1 versus the IECC? Do you definitely know the IECC better, about the same for both, or definitely know ASHRAE 90.1 better? Got the last couple of responses coming in here.
Okay, share those results.
All right. So the majority of you have used or seen the 90.1 compliance options. So that's good to see that fairly broad, but definitely those of you who have not, you are certainly not alone there either. Uh, does seem to have a leaning as far as knowing and understanding the IECC more, uh, with a few of you uh, definitely leaning more heavily on the ASHRAE 90.1. So thank you so much. Good to see the breadth of experience that we have. And with that, I'm going to turn it over to my colleague Sean for talking about what's in ASHRAE that you don't find in IECC.
Thank you very much, Ryan. So as Ryan mentioned, we're going to be covering a little bit about what ASHRAE has included in their standard that is not included in the IECC code. The first thing we're going to be looking at is for existing buildings, if you're replacing HVAC equipment, ASHRAE has an exception that allows like-for-like replacement in a special case condition where compliance isn't would require extensive revisions to other building systems, equipment, elements of the building. Uh, Something where you might see this is a somewhat larger building where you might have a large rooftop system with a VAV control system on it. If you're doing a like-for-like replacement, uh, under ASHRAE, if the previous system didn't have the same economizer controls, fault detection diagnostics, something like that, this might be an exception that applies there. Um, or if there's modifications that need to be made to that roof curb to comply with the energy code, a like for like replacement might be allowed to avoid having to do those major modifications to other systems in the building, such as the roof deck, um, any kind of power systems in the building, things like that. Where in the IECC, pretty much every HVAC system replacement needs to go through a sizing calculation, um, so that the equipment is properly sized for the loads in the buildings. Um, ASHRAE does have this limited exception here in special cases where that's going to create a severe problem with updating other components of the building system. Um, and you can then do a like for like replacement with that system. But like we've touched on before, many systems have excess capacity on buildings. And when the opportunity arises to do a like for like replacement, properly sizing that equipment may actually end up reducing its size and removing some of those additional requirements. And then you don't need to do a full explanation on why the full compliance isn't practical and try to get some waivers for that compliance path. And you're also likely to reduce the cost of that replacement. Downsizing that equipment is going to decrease that capital cost, which may mitigate the additional cost to do that additional load sizing calculation to begin with. So something to be aware of when looking at ASHRAE, that it does have this particular exception in limited cases that is not included in the IECC. Something else included in ASHRAE is a simplified HVAC performance path, which Ryan indicated in the HVAC flow chart that we looked at a couple slides ago. Um, it's again a specific use case situation. Um, the building has to be 2 stories or less above grade, has a gross floor area of less than 25,000 square feet, and each HVAC system does need to comply with a subsection of the ASHRAE code, section 6.3.2. But this essentially simplifies down your compliance from about 70 pages of HVAC compliance notes and subsections in 90.1 to about 2 pages of compliance checks. They do refer to some of those other sections in 90.1, so it's important to know what those are. So we're going to touch on those real quick here. But this path does allow you to avoid some of the more complex controls for smaller systems and smaller buildings where the added complexity isn't necessarily going to give you a big energy benefit for that facility. So looking at some of the specific requirements of that specific path, you're going to have single HVAC zones. The system should have variable flow or multi-stage fans if it's a larger than 5-ton system. Unitary package systems or split systems should have meet a minimum efficiency requirement. So again, all these things, these are compliance that's kind of typical for the full compliance path. These do have significant benefits even in smaller buildings such as economizers. But they're laying out specific points here that are going to maintain the efficiency of the system long term in the building, as well as the upfront installation, making sure that's as efficient as possible. Many systems are going to be qualify given their sizes. If we think back to what we mentioned about right sizing equipment, this may help the system meet requirements for the simplified HVAC system. So if you do right sizing and you downsize the size of the original HVAC system, it may then be able to fall into this simplified compliance path. So one example that we've kind of thought up is if the existing system was a 7.5-ton system, but can now be served by a 5-ton unit due to building improvements. That 5-ton unit is going to be less expensive than a 7-ton unit. You could use a single stage fan in a 5-ton unit, where the 7-ton unit might have a multi-stage fan in it. And the reduced airflow may also bring the unit under the threshold to require energy recovery systems. And so again, moving to this simplified path with a smaller system can lead to some potential energy upfront capital cost savings by removing some of these more complex requirements. So again, just a few more requirements in that simplified performance path. Many of these are good practice to include, such as avoiding simultaneous heating and cooling with reheat systems, making sure you can schedule those systems to match building schedules. This just goes back to not oversizing the equipment so that it can properly dehumidify, avoiding that simultaneous heating and cooling. We're also looking at properly balancing those systems with an air balancing process. Making sure that the design capacity of that system is going to be able to be delivered to the space effectively. And then also looking at adjusting the fan speed to the lowest speed that's going to provide adequate air to the least served space, which may be the furthest away from that air handler, off in the corner of a building, maybe a space that has high loads in it. So that's what we're looking at with a lot of these simplified performance path requirements, or these best practices that are going to optimize the system performance. A few more requirements here. Again, we're looking at those best practices. Outdoor air and exhaust, making sure those are adequately spaced away from each other, that you're providing adequate outdoor air and exhaust in the spaces of the building. If you've got separate heating and cooling systems, making sure there's an interlock so that they're not working simultaneously and fighting each other. Demand control ventilation still has some requirements that may apply here, unless the spaces themselves are small enough to be accepted from that provision. Um, Door switch controls is something that's also included here. We want to call out specifically those door switches for other building entrances which set the unit back if doors are left open. Um, some common example that I think a lot of people have seen are these restaurants that like to have these rolling overhead doors that can raise up, and now you've got an outdoor patio area when the weather is nice. You don't want the HVAC system still operating with that massive influx of outdoor air. So those overhead doors per ASHRAE are required to have a door switch that's going to deactivate the air conditioning system serving that space, because you've got adequate ventilation with the open building area. And you, again, you don't want to be conditioning that space when it's just going immediately out to the outdoors. Um, Another important thing is that the system needs to adjust to reduce the chance of the HVAC system operating when those doors are open. Um, so yeah, we've covered all that already. Looking at a couple of notes there that I thought I'd skipped over. One last thing that's included in ASHRAE, specifically related to air movement and things that's not included in the IECC, is that you're required to have data on overhead ceiling fans based on the airflow and the power at max speed. There are no requirements for these fans, but you're required to have documentation of their performance. Um, which is an interesting thing that I think they're setting up for future provisions in the code, where they're going to want to have performance requirements for these fans. Right now, they're just prepping people to document that information and make sure that it's sent to the code officials. Um, One of the things that we've noted is frequently these are only operated at full speed during the summer, and then at reduced speed during the winter to provide destratification to a space while minimizing the wind chill factor, particularly in the winter time. In the summertime, that wind chill factor can actually be a benefit that helps reduce your cooling loads. Um, but at this time, again, we're noting there's no required efficiency requirement for these fans. They're just requiring some documentation of what you're installing in the space, what those designs are. Having a published span, airflow, and power may enable future energy efficiency requirements to be established. And so part of this may also be, as we're documenting this, they can use that information for research into what those future requirements might be to optimize the efficiency of these systems. Something else that ASHRAE includes that IECC does not is dehumidification requirements. For this and humidification, there are exceptions, such as specific zones in a building that require specific humidity levels, such as museums, hospitals, certain areas that have these specific really tight tolerances for the purposes of running tests or optimizing the healthcare environment, things like that. But those areas do have to be specifically approved by the authority having jurisdiction to be accepted from the dehumidification requirements. Humidification and dehumidification can be very energy intensive, so it's good to understand why we're requiring these dehumidification in ASHRAE and how tight the tolerance is. We're looking at mechanical cooling should be controlling to a dew point of 55 with about a 10% dead band, and the humidity set point of 60% with about a 5% set point range there. So commonly the goal for that relative humidity is to keep it between 60% and 40%. In the winter time, you're looking more at that 40% so that you're not having condensation on the windows, things like that. In the summertime, you may get up to about 60%, but more commonly trying to keep it in that 55% range for comfort reasons. But what we see in a lot of buildings is that, particularly in the wintertime, humidification can get particularly low in a building. And we'll touch on that on this next slide, where there are humidification requirements as well. Fossil fuel and electricity shall not be used to produce relative humidity above 30% in the warmest zone served by the system. So again, we're setting these limits where we're not using excessive energy and adding excessive humidity back into the buildings. That 30% minimum requirement from studies and things optimizes kind of the healthy conditions in the building. Again, you're avoiding any kind of condensation on surfaces, particularly in the winter time, minimizing dust mites and things like that. And so we've got these tight tolerances for dehumidification and humidification to optimize that energy performance and again avoid any kind of issues that they might cause in a building. The other thing we're looking at is providing adequate safety against the risk of static discharges in facilities, particularly where you've got electronics. And so again, that's where those allowances are coming for specialty situations, such as archives and other preservation methods. There are exceptions for those where the relative humidity might need to be a little bit higher than 30%. Those exceptions are included in ASHRAE. We did get a question, isn't that 60% too close to the mold threshold? In the summertime, it's getting close. And so again, we usually see most designs are targeting that 55% relative humidity range. But usually with most cooling coils, the design dew point coming off of those is somewhere between 55 and 60 Fahrenheit. And so depending what the temperature you're keeping within the building, particularly if you're keeping it a little bit cooler in the summertime, you might get close to that 60% threshold. So I believe 65% is where you really get a large increase in that risk. But yeah, 60% is pretty close to that threshold. So thank you for that question. We also had another question come in regarding ASHRAE using that 60% as a minimum threshold. Is that the coldest zone? I would believe that would be the correct choice, because if you're applying that to an average across the building, that coldest zone would be above that 60% relative humidity threshold. So a couple of good questions there about that. But yes, you want to make sure that when you're doing these designs, the ASHRAE's limits are kind of that giving you the widest band possible for allowing a little bit of design flexibility while still maintaining safety. So while that 60% is getting close, there is a lot of research that, about 65% relative humidity is where that risk really goes up. 60%, you're kind of on that borderline where a lot of designers for safety reasons will go lower than that. Next thing that ASHRAE includes is a requirement for direct digital controls for particular applications. So where the IECC might allow for just programmable thermostats on systems with scheduling, there are certain areas where ASHRAE requires a full DDC system that meets some minimum requirements listed in that section of ASHRAE. Excuse me. But as far as when DDC is required, the system or plant needs to serve at least 3 zones and a fan system brake horsepower of larger than 10 horsepower. So you're looking at a pretty significant size system here that's going to have significant energy consumption. You're going to want to be able to optimize multiple zones on it to minimize its energy consumption. For alterations and additions, if one needs to extend an existing DDC system to cover a new area, if it falls within these requirements, that might be something to look into for your project. You may trigger this requirement in a renovation. But a DDC system does need to be installed if you're replacing boilers and chillers that are part of that renovation. They'll need to have DDC controls if they're larger than 300,000 BTUs per hour. So just a few of the larger requirements on system sizing. As far as what the specific requirements are, we won't get into those in too much detail here, just due to time limitations. but being aware that this is something that's added in, that the IECC allows a little bit simpler um, compliance path with programmable thermostats, um, that ASHRAE gets a little bit more stringent on here. Another thing is chiller plant monitoring. The IECC doesn't currently include this in it. We expect to see this in future versions, but keeping track of what your chiller plant is actually doing, and making sure that it's maintaining its efficiency throughout its operation, baselining that efficiency, um, is an important component of making sure the overall building efficiency is maintained. So larger plants do need to be monitored for energy consumption and efficiency. Um, some of this may already be available through onboard controls and panels on chillers, but the importance is understanding the accessibility of that data to plant operators to monitor that efficiency over time. Um, so you do need to have electric and efficiency measurements for those chiller systems recorded at least every 15 minutes and maintained over a 36-month period, so that you have reference to go back to, so you can see past chiller operation, and understand how that efficiency is being maintained over time. And it also helps you catch if a problem has occurred that maybe hasn't shown up as a maintenance issue yet. Your efficiency starts to decrease. It's a good indication that there's a mechanical problem somewhere that needs to be investigated and corrected. For campuses or other large facilities that may have multiple chillers, understanding which chillers are most efficient can also be a useful energy management strategy. If you've got multiple chillers on site, um, there may be some trade-offs between, when you hit a certain load capacity, maybe these larger chillers are more efficient at higher capacity, but as they drop down in load, then it's time to switch to a smaller chiller that's more efficient at lower load. And so, again, um, chiller plant monitoring, again, it's just that optimization process that's being included here. So yes, a couple of questions have come in here. If you're designing to IECC in an existing building and you switch to ASHRAE, um, and then it falls within this chiller plant monitoring thing as you're doing compliance with an ASHRAE project in an existing building, then I believe this could be triggered as well for that particular project. Ryan, I don't know if you can look that up and verify that
Yeah.
while we're going on.
Projects need to follow compliance of one or the other. If you do have uh, and that's on a project by project basis. So if you if you have an existing building that may have been built to the IECC and you're now doing a project and the project is doing ASHRAE 90.1 compliance, that is permitted, even though the building may have been IECC originally. But again, this goes back to project by project. What you we what is not permitted is say, okay, we're going to do, we're doing a project that's going to, we want the HVAC to be done under ASHRAE 90.1 and we want the lighting to be done under IECC. That's not permitted. So you have to choose one or the other, but it is on a project basis.
Correct. Yeah, and if you had a building that was previously under ASHRAE and now you're renovating under IECC, you wouldn't have to then worry about these requirements. If it's already in place, it's there, that's great. It's beneficial for the building. But as IECC doesn't currently requirement, you don't have to then update it because there's no IECC requirement for that project. So
And
yeah,
compliance is a minimum standard. There's nothing that if you're doing IECC compliance and projects find it's good practice to monitor the electric and efficiency of chillers, that is perfectly acceptable and excellent to do.
can always go beyond what the minimum is. Something else that ASHRAE includes, IECC does not, is an occupied zone standby setting. So zones with only auto off lighting controls, and 62.1 occupancy permits ventilation to go to zero when in occupied standby. So looking at ASHRAE's ventilation standard 62.1 there. In certain spaces, they do allow that ventilation to drop when a space is verified as unoccupied by a monitoring sensor. So after that 5-minute period of being vacated, then the heating and cooling set points should set back by 1 degree Fahrenheit, and the airflow can be at zero when it's in the deadband range for that temperature set point. Something that they're working to provide here is setback of zones when there's no occupants present. So you can do this through the same control as you would lighting, and save on kind of purchasing a separate sensor, or you might have a separate sensor for the HVAC, depending on how your system is laid out, what kind of lighting control system you're using. I would recommend that you use the same control signal as the lighting system, because if the lighting occupant sensor fails and the lights don't kick on in the space for some reason, the occupants are going to report that and get it quickly fixed. Where if you have a separate HVAC sensor that fails, people might not notice that 1 degree difference in the space that the space is set back to. Although if they're in that dead band for a significantly long period, they might notice that it gets a little stuffy in there. But that might not necessarily be noticed as something that's an actual mechanical failure. So we do recommend, where possible, as much as possible, tying this kind of occupied standby control to the lighting sensor to make sure that it's caught and maintained in a timely fashion. As we noted earlier, the minimum deadband is 5 degrees. We've covered this in our IECC conversations. It's also in the ASHRAE. So you've got that 5-degree deadband that prevents simultaneous heating and cooling. So if you've got a 1 degree offset and then a 5-degree deadband, again, occupants aren't necessarily going to notice that 1 degree setback. But the other thing they're trying to do here is, when it's doing this setback, it's trying to be something that can be recovered from quickly when an occupant walks back into that space. So again, it's going to be something that's not noticeable to the occupants, but then can be quickly recovered, and is still going to provide energy savings by, you're reducing that airflow to an unoccupied space. So you're backing off the VFD for that fan and saving that fan energy. Restrooms are a different case. Mainly because there is exhaust out of those restrooms that's required separate from the heating and cooling ventilation air. I do know in some situations, those for small, like private bathrooms, those exhaust fans can be tied to an occupancy sensor that turns off the individual fan in that restroom. I don't believe you can do that with larger multi-unit restrooms. I'll have to check and verify that. But if you're pulling continuous exhaust out of the space, you definitely don't want to be doing a setback that turns off the airflow and then creates pressure problems, where you might have issues with the doors to that restroom now, because you're exhausting air out without supplying makeup air to the space. We'll check and verify that for larger multiple unit bathrooms, whether that's an applicable thing that can be done if you're controlling both the supply and exhaust and balancing that. I wouldn't recommend it though, as you can still get odors building up in that space. Supply temp reheat limits. ASHRAE has a reheat supply temperature limit that's meant to limit the effects of stratification of air. That's not included in the IECC. So where reheat is permitted and supply and return openings are more than 6 feet off the floor, the supply temperature is limited to not more than 20 degrees above the room temperature set point. Again, the reason for this is they're minimizing that potential for stratification of that reheat air, where you've got hot air at the ceiling that's not actually reaching down to the occupant level, And so you're exhausting that warmer air out of the space before it impacts the comfort of the occupant. ASHRAE is trying to control that here through maintaining that temperature difference, where a lot of designs, um, they increase the minimum reheat airflow to combat that stratification issue. So again, we're looking at minimizing the fan energy here. And since you're also minimizing that reheat energy that's being used for that temperature difference, you're minimizing two sources of additional energy for the space. Um, we had a question come in for the occupied standby. Are there provisions that allow the zone to turn on when humidity rises above set point? Since there are humidity control set points in ASHRAE and others, I expect that that is the case. And I believe that would be contained in the actual humidity control sections of ASHRAE, since the actual occupancy sensor section only references temperature. I would look at the humidity control sections in the code and see if there is something there that overrides that particular occupied standby setting. And again, even if it's not specifically mentioned there, most of these codes do have language protecting the health and safety of the building. And so if you needed to set that kind of control up, a code official could be convinced to accept that kind of setting based on that health and safety language that's in ASHRAE for maintaining the healthy building environment. Something else that's included for humidification systems, this is looking at larger humidification systems. Preheating jackets shall be automatically turned off when humidification is not required. That way you're not adding heat to the airstream, and you're not kind of doing an unintentional simultaneous heating and cooling with this humidification system. And dispersion tube hot surfaces should be insulated to at least an R.5. Again, combating that risk for potential simultaneous heating and cooling. And preheat coils should stop heating output when mechanical cooling is occurring. So again, all these features are making sense for preventing that simultaneous heating and cooling in the system. So what we're understanding here is that when humidification is not needed, the source of heating should be turned off. Similarly, when you're operating mechanical cooling, preheat coils or freeze protection coils are sometimes used to add a false load to the system to assist in dehumidification. ASHRAE is saying here you cannot do that. They're relying more on controlling the airflow speed across that coil to achieve your dehumidification. So they're forcing you here to look more at the airflow design of the system and rely less on kind of these more energy intensive methods for putting false loads on the cooling system to assist with dehumidification processes. Next thing is pipe sizing for ASHRAE. Chilled water and condenser piping is designed to limit velocity. There's a table in the energy code that, depending on the size of the system and piping layouts, ranges from 5 to 13 feet per second. Sorry, runtime, and whether the flow is variable or not. So here ASHRAE is looking kind of beyond those typical pipe sizing and design practices and is going a step further for sizing chilled water and condensing piping. Limiting velocity can limit the pressure drop per foot of pipe, which is going to save you on pumping energy. Can also have an impact on chiller performance. Limiting the bends and minimizing the equivalent pipe length is going to further reduce the pressure drop, which may enable smaller pumps to be used. as well. The lower, uh, the photo that we've shown here, most chiller plants, you see an optimized space design where you've got 90-degree bends in the piping to limit the footprint of chiller systems. Here they've opted for 45-degree bends or less. Looks like these may be even 30-degree bends. Um, so they're limiting again that frictional impact that those fittings have on the flow of that fluid. Um, and so again, ASHRAE here is just looking at that in terms of the flow rate through that piping. And so looking at designs and things that are going to maintain that flow rate may lead you to these reduced angle fittings, and you're trading off a little bit of the floor footprint for a building for this higher efficiency, but with design of equipment and things, you can kind of compensate for the pipework taking up more area by fitting smaller pieces of equipment under these lower heading areas of the pipes. Coil selection, something that ASHRAE has included here is that chilled water coils have to have at least a 15-degree Fahrenheit delta and a leaving water temperature of at least 57 degrees Fahrenheit at design conditions. Typical design we see is a 10-degree delta for cooling coils. There are exceptions for constant air volume systems, smaller systems of 5,000 CFM or less, and some less common applications. We won't necessarily get into that list of all those, but so again, what we're looking at here, you get a little bit better humidity control with the higher delta T. We also see that off design conditions, if you're designing for a 10-degree Fahrenheit and you get that cooler chilled water going back to the chiller, that decreases the chiller's efficiency. So maintaining this warmer water temperature, you're maintaining that better efficiency, and you're also getting better part load operation out of your systems when you're not at design. You can also reduce the pumping required in your chilled water system as those coils absorb more heat than they would with a 10-degree design per unit of flow. Um, you also reduce the chance that the low delta T coming back to the chiller limits that chiller's output. So on top of the efficiency decrease from having colder water come back to the chiller can also limit the capacity of that system. So again, looking for kind of these minor things we don't necessarily always think about that have a pretty large impact on overall plant efficiency and operation. Something to be aware of, looking at this, most chillers have a capacity based on a 10-degree differential between the supply and return. So again, if at part load conditions, you've got a coil that was designed for 10 degrees, at part load, you may only have a 5-degree difference. Now your chiller is not working at the design differential it was set to. And so by having this 15-degree differential built in at design conditions, you're more than likely to hit that 10-degree differential at part load conditions and maintain your chiller's performance. I went the wrong way. Similar thing for high capacity space heating. Here they're looking at most new large boilers are the condensing type boiler. The issue you run into with a lot of these is that return water temperature gets warmer, and then they cannot operate as well in the condensing range. You got to have that cooler return water temperature to maintain the high efficiency in the condensing operation of these condensing boilers. So you do have, for 1 to 10 million BTU units, the return water temperature is limited to 120 degree Fahrenheit or lower for the design of the system. And we just included a chart here that shows you that impact on return water temperature on the efficiency of the system. You can see once you get above between that 120 to 130 range is where you start seeing that efficiency really kind of trail off and get to those lower 80%, upper 80% efficiency ranges. So to maintain that higher efficiency, you really want that cooler return water temperature. And so here, the reason it's focused on high capacity systems, You're looking at a few percentage points of efficiency increase on a smaller system. That may not be a lot, but if you're looking at a 1 million BTU system, that's an extra 15,000 to 30,000 BTUs per hour of output from that efficiency increase on that system. Looking at exhaust air energy recovery, ASHRAE has different requirements. This is actually in the incorrect section. But ASHRAE and IECC both have exhaust air energy recovery requirements. The IECC requires a 50% enthalpy recovery ratio. ASHRAE's is 60%, so it's a little bit higher. My apologies that we've got this in the wrong section here, but it should have been in our next section where we're comparing the IECC and ASHRAE's requirements. Looking at surface water heat energy recovery, ASHRAE, we're looking at recovering condenser heat for surface water heating here. Surface water heating energy recovery is not required too often, as 1 million BTU per hour water heating is a lot of surface hot water. So what we're looking at here is mainly using that heat recovery off of the main HVAC chiller condenser, using that for your surface water heating. Not likely to apply to a lot of facilities, but where you've got 24-hour operation, you've got a large load for domestic water on a continuous basis. That's where this requirement is triggered. You're mainly looking at here hospitals or larger facilities that include residences where people are constantly in that facility. You might also consider using heat pumps either as an air source or water source heat pumps, even if not required. So what we're looking at here is using these cooling systems instead of rejecting that heat straight to outside, doing a little bit of energy recovery on systems where you've got a large continuous demand for service hot water heating. Space conditioning heat recovery is also required by ASHRAE. It's not specifically laid out in the IECC. Again, we're looking at heat recovery chillers for larger systems that have simultaneous heating and cooling needs. So we're providing that low-cost heating or low-cost cooling, depending on the perspective that you're looking at here. But a condenser heat recovery shall supply 7% of the cooling capacity for the overall system. And then you're also getting that heat recovery supplying heating to the building. And it could be used for reheat purposes. Some examples here: inpatient hospital operating 24/7. It's a good option for that. Actually, it's one of the situations where this is a requirement. Where your design chilled water capacity is greater than 3.6 million BTUs per hour, or where simultaneous heating and cooling occurs above 60° Fahrenheit outside air temperature. So where you've got a building that has specific dehumidification loads, that's going to require cooling to dehumidify and then heating to reheat back to comfort temperatures. Pool dehumidifier energy recovery. Pool dehumidification is one of those areas that requires a lot of energy as you're trying to manage a lot of latent load there. It can also increase chemical use. If the humidity is driven too low, you get a lot of excess evaporation off the pool den. As you replace the water, you also have to replace the chemicals to maintain the balance in the system. So ASHRAE does require energy recovery at a fairly low threshold of only a 500 square foot natatorium space. So if your indoor pool is over 500 square feet, with dehumidification control, you should have a sensible exhaust or total energy recovery of at least 50%, or condenser heat recovery to use 100% for pool heating when needed. So we're looking at designs here. We'll likely select the first method of energy recovery. it's a little bit more difficult to connect the condenser to the pool heating and get energy recovery from the system supplying the pool heat as well. It's a little bit more complex to run that piping, a little bit more expensive. Um, so that first option, doing exhaust sensible heat or total energy recovery, is a little more economical, a little bit easier to achieve. As we touched on earlier, with the simplified HVAC method, there are door switch control requirements. So in ASHRAE, you do have this requirement as well, just covering that specifically. In a conditioned space with a door that's opening to the outdoors, its space should be provided with controls when the door is open to disable heating or lower the set point of heating to 55 degrees or lower. Disable the cooling or raise the set point to 90 degrees or higher. And then this excludes entries with automatic closing devices. So that way you're not required to do this for like your general use lobbies or something like that. What you're looking at here is, again, the example we gave: restaurants with overhead doors, patio spaces. They can open those patios up on mild days to outdoor seating. That's where these door switch controls are primarily used. Again, we want to note here that this isn't disabling the heating and cooling systems. It does have that option to do heating or cooling at a moderate temperature, that set point of 55, 90 for heating and cooling set points. So you do still have some ability to do ventilation, air movement, particularly if you're in a patio area that maybe not exposed to direct wind. That may be something to look at here. Instead of disabling the heating, you just lower the set point to this, and then you've got your ability to move air still. IT loads, ASHRAE has a standard for data centers, 90.4. But HVAC serving only a computer room with a load greater than 10 kilowatts shall use that standard for its design. So that's what's being referred to here. It's good to understand where the threshold is between a room with IT equipment and a data center. Buildings commonly have several IT equipment rooms that contain equipment such as switches and servers, but those would not be considered data centers. This is specific to data centers. And again, it's that equipment load greater than 10 kilowatts. And one of the last ASHRAE specific requirements is duct installation in indirectly conditioned spaces. So ASHRAE has recommendations for this. Where we particularly see this is return air plenums above drop tile ceilings. The duct installation requirements, for the most part, match the IECC in most situations. You've got that R6 for interior ducts, and R8 to R12, depending on which climate zone you're in. ASHRAE includes indirectly conditioned spaces that is not included in the IECC. So they've added in this separate requirement here for indirectly conditioned space insulation requirements. And they require an R1.9 insulation level on these ducts. Return duct insulation is not required in indirectly conditioned spaces, mainly due to the fact that the return duct is pulling air from the indirectly conditioned space. The air temperature in the duct and in the indirectly conditioned space should be about the same. But on the supply side, you do have a temperature difference there that can, in some situations, lead to condensation. And you're also just losing some heat in a space that's not impacting the comfort of the occupants. And so on the supply side, you do have to have that R1.9 duct insulation in an indirectly conditioned space, such as an above ceiling plenum. As we noted, we've come across several locations where that insulation is either not installed, either following the IECC, where that space is considered a fully conditioned space. And due to duct leaks or outdoor air leakage into that plenum space, then you end up with condensation. And then you've got maintenance people looking for roof leaks that aren't there because the ceiling tile keeps getting wet, but it's coming off the ductwork. So that's the last of the ASHRAE specific requirements. We've got a poll question to launch here, and we'll touch on a couple more of the questions that have come in while you're answering the poll questions. So our first question is, for a 4-story building above grade, 25,000 square foot, can that use the simplified HVAC approach? Again, it's a 4-story above grade building, 25,000 square foot. How far back must a chiller plant monitoring data extend to comply with the 90.1 requirement? 1 year, 2 year, 3 year, or 4 years? Let's see a couple of questions that we've had come in here. One is, does ASHRAE require condensing boilers on systems over 300,000 kBTU? We are seeing owners shift to non-condensing for the reduced maintenance and issues. I don't have it pulled up right in front of me. Ryan, do you have access to that?
Yeah. ASHRAE is preempted by federal law from requiring equipment efficiencies above the federal minimum standards. So both ASHRAE 90.1 and IECC, the minimum equipment efficiency standards is the same as the federal government due to preemption. So that is something where you're definitely keying in on one of the potential concerns going forward as you know, energy codes move faster than legislation as far as being able to provide efficiency.
Yeah, and so that ASHRAE requirement for the minimum condensing temperature applies where a condensing system is installed. I believe that that specific requirement had that 300,000 limit, but not the requirement to install a condensing boiler. Just the requirement to have that minimum condensing temperature of 120 degrees. Or sorry, maximum condensing, or returning water temperature. Okay, looks like most of our responses have come into the poll questions. The correct answer to question number 1 is false. It has to be 2 stories or less to qualify for that simplified HVAC approach. And 25,000 square foot is right at that maximum limit for square footage. So the correct answer there is false. Being 4 stories, it exceeds that simplified approach requirement. How far back does the chiller plant monitoring data have to extend? The correct answer there is 3 years, noted on our slide, 36 months for tracking usage history and efficiency data. It looks like most people got those correct. It's a little bit of a split on the chiller plant monitoring. Okay, I believe I'll hand it over to Ryan to go over the ASHRAE and IECC comparisons where they are similar, but slightly different in ASHRAE.
All right. As far as our existing equipment, you know, understanding that most HVAC systems do have some excess capacity that can be used to serve an addition, and we have touched on this in the past, as perhaps identifying extra capacity through the use of runtime, which can be available either through data streams or perhaps a building automation system or smart thermostats. Alternatively, you might also look to the ASHRAE standard 183 as far as trying to identify potential additional capacity, particularly as buildings during their lifetime may have gone through updates and improvements. Quite often you'll see a lighting improvement reduce loads. And so while the system may have been designed for through 183 in the past, a new 183 model may show that there's now capacity where there wasn't before. So, uh, both ASHRAE and IECC do have very similar standards or similarities as far as thermostat settings and what has to be done there, dead bands and the like. Uh, so that's fairly similar. However, these setbacks can be rather dramatically different between the two. ASHRAE is a much more relaxed standard, stating setback of 10 degrees on the heating side and 5 degrees for the cooling. Uh, Radiant systems do have a little bit of a tighter tolerance of 4, predominantly because first, they're not generally run quite as high, and second, recovery may be slower. So IECC has a much more stringent setback of 55 and 85. So that's rather dramatic there. So that's a big difference between the two. As far as the setback control options, the ASHRAE standard splits the setback requirements from the shutdown, whereas the IECC marries those two together, setback and shutdown controls. And you see here there's a few differences. ASHRAE, using occupant sensing devices or manual timers and interlocks with security systems. IECC is much more prescriptive as far as scheduling and overrides and backups. So that's something to be aware of, particularly the setback and shutdown. ASHRAE splits that into two separate areas, and IECC keeps them as one. So, as far as optimum start, ASHRAE calls out they're much more specific as far as the parameters used for the optimum start. IECC just states that you need to have optimum start time. And something I will note here is both of these are very temperature focused, and understanding that humidity does have an impact on comfort, and as we've kind of touched on a few different times here today, as far as humidity and the potential for mold if we're not properly uh, controlling for that. Uh, so frequently that may be a symptom of a larger issue of oversized equipment where we haven't been able to drive that moisture out of the air far enough away from that 60% limit that we really want to stay under. So motorized damper leakage is a little different between the two. Uh, ASHRAE has differences depending on if you're in the warmer zone 4 or the cooler zone 5 of 10 and 4 CFM per square foot respectively. The IECC just calls it out and says it needs to be 4 CFM per square foot and you're done. Uh, so as far as parking garages and their ventilation system, ASHRAE has a requirement to stage or modulate to 50% or less capacity. IECC is similar in staging or modulating to 50%, or IECC also has the ability to intermittently operate the fans at least in less than 20% of the time or as needed to maintain that. Part of this goes back to if you have a parking garage with a single fan, trying to stage or modulate that can be much harder, whereas under IECC, just being able to intermittently operate that may be a little bit easier. So with that, they also have a little bit difference as far as the exceptions go. For parking garages, ASHRAE, the exception is for, they have exceptions for small parking garages, as well as looking at the square foot of parking garage per horsepower of energy, and that they have no heating or mechanical cooling. IECC their exception is based on certain CFM per horsepower. So this is based on the fan efficiency curve for the IECC, where ASHRAE is more based on power intensity. And noting here the difference between ASHRAE at 30,000 square foot and IECC at 22.5. So again, a little bit different there. Here noting that we've got several different exceptions for demand control ventilations or DCV. IECC has a higher threshold for DCV than ASHRAE does. However, ASHRAE does exclude DCV for several occupancy categories. Some of these may include, correctional cells, daycare, sick rooms, science labs, barbers, beauty and nail salons, and bowling alley seating. So that's where ASHRAE, if you're in some of these special occupancies, you may have DCV exceptions on those, which can be useful to you. So, as far as the economizer exceptions, there are some little bit of differences here. ASHRAE has a much higher threshold in order to use that than the IECC. However, something you'll see here is ASHRAE has economizer exceptions for both zone 4 and 5, whereas IECC, even though it's a much lower threshold to get that exception, it is only in zone 4A. So if you're in the Chicago region, IECC does not have the economizer exception, whereas ASHRAE does, despite having to have quite an increase, a 49% increase in efficiency in order to gain that exception. So quite dramatic here for the Chicagoland area and Rockford area, that northern Illinois area. As far as fan efficiency, here we get into a little bit of a nuance between the two. Between ASHRAE, they're using something called the fan efficiency index, whereas the IECC uses the fan efficiency grade. So a fan efficiency index for ASHRAE, as you can see, it can go above 1.0 or 100%. And so what that's kind of looking at is how it's doing relative to a theoretical reference, whereas the fan efficiency grade tops out at 100. As far as our hot gas bypass limits, ASHRAE, here again, it has a much tighter and more stringent limit as far as using hot gas bypass, because really hot gas bypass is just adding a false load when the system has low loads on it. So likely to occur when you have relatively cool days without a lot of occupant load. But providing economizer through, or providing the cooling through the economizer is going to be much less costly than operating mechanical cooling and then adding that false load onto it. So an alternative that you might consider is looking at multi-stage units. So a 15-ton unit might come with either a pair of 7.5-ton stages, or some of them are designed with a 5-ton and a 10-ton stage. So some of that may be equipment selection as far as how you can avoid some of these needs for it, rather than having to falsely load the system. As far as variable flow controls, both ASHRAE and IECC require variable flow controls. ASHRAE states for systems with 3 or more control valves must be variable flow, whereas the IECC has a threshold of at least 300,000 BTU to be variable flow. So there can be a few different methods that you might handle this. One of these might be either using one three-way valve in the whole system to uh, make sure there's that minimum flow rate for proper operation. Uh, or another method is installing a bypass valve that modulates if the flow gets too low. So having that ability to modulate while maintaining uh, that minimum flow for proper operation. So with that, I think we're got another poll here before we transition over to service water heating.
No, this poll is specific to the service water heating, so it'll come up later.
Oh, okay.
All right, so looking at our service water heating requirements, touch on these. Service water heating, ASHRAE does require a load calculation done for service water heating to size the water heater. That's not included in the IECC. So similar to the building HVAC system, it's important to size the surface water heating equipment properly to maintain that peak efficiency. Oversized equipment is going to lose that excess heat to standby losses and to losses out the vent stack for gas equipment. For facilities such as the one pictured here, where there's a couple of storage tanks, you could try to isolate one or more to see if all the tanks are still required based on current operation. Usually new water fixtures are installed. They're going to be using less flow than previous fixtures. And so if you're renovating a building that has multiple water tanks, you may be able to get away just by isolating a storage tank that's not needed. They may also find that instead of isolating one tank, they may find that one tank meets the needs most of the time, and then the other tank is used for peaking flows. This allows for options such as further addressing loads so that one tank can handle the loads, or downsizing the existing tanks so when the time comes for replacement, so instead of having maybe 200-gallon tanks there, they go to a pair of 75-gallon tanks. So what we're looking at here again is just sizing these so that you're meeting that building load throughout the day, and that you're using that equipment without excess losses to standby losses, vent losses out the flue stack. Service water heating temperature limits in ASHRAE are not included in the IECC. So at the faucet, you have to have 120 Fahrenheit water or lower as needed for intended use, and 110 for public lavatories. So ASHRAE places fairly strict limits here. This not only saves energy, but it reduces the potential for scalding injuries from overheated water. Facilities with at-risk populations where you're worried about Legionella, you may be able to run higher service water temperatures, but you've got to have that mixing valve then to get that water down to these set point temperatures in the distribution system. Facilities with at-risk populations, yeah, just covered that. So yeah. While both ASHRAE and IECC have requirements for time switch controls, ASHRAE is much looser, only specifying that time switches or other automatic controls are needed to turn off service water systems when there's not a requirement. The IECC has a little bit more stringent requirements, specifying the cycling of the pump, including turning the pump on when there's a call for water, hot water, and turning it off when both the call is absent and the service line has been charged to the service temperature, which is typically sensed by a temperature sensor on the return line. We've spoken a lot about that in our IECC presentations. This is one of those instances where the IECC is a little bit more stringent than ASHRAE, where usually the ASHRAE standard is a little bit more stringent than the IECC. So what we're looking at here is in the IECC, they have specifications for hot water circulation systems and demand hot water circulation. Those two requirements are requiring those pumps to turn on and off based on that hot water demand. Where ASHRAE does allow the use of time switches where you can do hot water service based on a building schedule. For pool covers, what we see here is a substantial difference between ASHRAE and the IECC. ASHRAE requires pool covers for both indoor and outdoor pools, whereas the IECC only requires it for outdoor heated pools. For warmer pools, such as therapy pools, the cover must have an increased insulation value, that R12 that's noted there. So the main thing we're looking at here, again, you're predominantly reducing evaporation from those pools, which increases that heating load and also increases chemical replacement costs as well. Looking at shared equipment here, ASHRAE prefers to avoid sharing heating equipment between space heating and service water heating. We do sometimes see this in heating systems that use boilers that may contain a domestic hot water generating coil attached to that boiler system. The primary reason is to avoid bringing on a large boiler system intended for heating the entire space of the building to serve that relatively small domestic service hot water load. And so here, ASHRAE has provisions for equipment that can serve both heating loads. You have to have the low standby losses. You demonstrate savings over having the units operate separately, and the total capacity has to be less than that 150,000 BTU per hour temperature or capacity limit. Once you get into larger systems, they really do mandate that you have separate domestic hot water from the space heating system. Again, it's just that large disparity in the loads doesn't allow that large HVAC system to supply such a small load very efficiently. In heated pipe length, this is one situation where the IECC has a requirement that ASHRAE does not. So what we're looking at here is in the IECC, you've got that supply volume limit for public lavatories at 2 ounces, and for all other service hot water connections, it's that half-gallon connection. As one can see, the requirement for about a half-inch pipe would have to be within 2 feet of a public lavatory, so that the circulating system has to be fairly close. With newer half-gallon per minute faucet aerators, that flow rate is only about 1 ounce per second. So with the seemingly minute 2 ounce allotment, that's still 2 seconds from when the tap is turned on before hot water arrives, which may not seem like a long time unless you're standing there waiting for it. So here the ASHRAE is taking in that consideration in how much cold water, stagnant water is in that hot water line. It has to be passed out before hot water reaches that service faucet. And then for existing buildings, replacement equipment needs to meet the same requirements as new construction without requiring alterations to building systems outside the scope of that alteration or replacement. So if you're working on an air handler, the requirements apply to that air handler. If you're working on a service hot water system, it applies to that hot water storage tank system, not necessarily circulation piping and stuff if that's not being touched. So we will launch our last poll here. The question is, ASHRAE has more specific service water requirements in which area? Load calculations, temperature controls, pool covers, or pipe length? There are 2 correct answers here. We did have a couple of questions come in through the chat, I believe. For setbacks, what are the setback requirements for ground source applications? Typically, large setbacks overload the bore field and geothermal systems. I have run across that in the past looking at buildings. I don't believe either standard um, specifies a difference for geothermal systems versus uh, kind of your standard gas and chilled water, hot water type systems um, for those setback requirements. But that is true. We have run across geothermal applications where, um, particularly in extremely cold weather, those bore fields get shocked with that cold water, and the pumping systems have to turn down temporarily and then restart. And that causes some delays in recovery rates and stuff. But yeah, I haven't noted that either code has specific exceptions for geothermal systems for those setbacks.
That may be where the application of radiant heating might also be useful there under ASHRAE 90.1, because radiant heating only has a 4-degree setback requirement versus a 10. So you going towards a radiant panel, which, as I recall, commonly is a more efficient delivery mechanism than forced air too, can be useful in that regard.
Okay, looks like our poll question has got all its answers in, so we'll share those results. The correct answer is ASHRAE has more specific service water requirements for load calculations. You have to have proper sizing of that system that IECC doesn't cover, and pool covers. It's got the additional insulation, and the covers have to be on interior and exterior pools, where the IEC only requires on exterior heated pools. As far as temperature controls, the IECC is a little bit more stringent there as far as controls and circulation, and then pipe length, um, where the pipe length requirements are in the IECC but are not in ASHRAE. I did have a question about for the chilled water leaving temperature um, at least 57 degrees. Isn't that going to cause dehumidification issues, because chilled water below 50 Fahrenheit is usually what's used for that dehumidification? Um, so what you're mainly looking at there is the average temperature across the coil. Um, if you've got inlet water temperature coming in at say 48 degrees or so like that, if it's then leaving at 57, most of that coil is still going to be able to provide dehumidification, particularly if it's a coil that's set up with a couple of banks in series. That first section of the coil is going to do your primary dehumidification, and then as the water warms, then you're getting your sensible correction to the air after that off of those. So it does take a little bit of design for those chilled water coils to ensure you get dehumidification with those warmer leaving temperatures. But again, that comes into with that coil delta T design as well. Kind of impacts how that dehumidification works as well. And then we had a question about I believe this is the unoccupied standby. Is that a requirement and not an option, correct? It is one of the prescriptive requirements in ASHRAE. So if you're following that prescriptive performance path, then yes, it would be a requirement for those spaces. It is not a mandatory requirement though, so it doesn't have to be done if you're doing one of the other performance paths. See if any more questions came into the chat. We had a couple questions about PDF availability. Yes, we will have a PDF available of these slides for download from our website. I believe it also gets sent out with the certificates, doesn't it, Ryan? or
I
do we have
believe
a link to it?
yes. If not, it will be available on our website along with the archive of today's recording presentation. So you can see archive copies of all of our past webinars and workshops along with the PDFs of their slide decks as well. So do want to thank everyone for their participation today, and hope everyone has a great afternoon, and we look forward to seeing you on our next session in November.
And again, if you have questions, please feel free to reach out to us at energycode@illinois.edu or through that 1-800 number. Thank you all for attending today. Hope you have a wonderful afternoon.